thing I want to talk about is, I think that the brain has to be the most fascinating thing out of all of the ones that I mentioned before. And so, again, I don't want to give too much structure here. Maybe Evan, I'll let you start with, how do you see the interaction between the brain and the three other kind of big physiological systems that I mentioned? So if I say brain and heart, what do you think? If I say brain and lungs, what do you think? And then brain and muscle, and maybe give a little bit of a baseline on this. And then Pat, I'll let you go after that same question as well.
Yeah, for sure. So, I mean, given that you're talking about the relationship between the brain and all of these other systems, like the first thing that comes to my mind is just thinking about like integrated cardiovascular control. So I'm not an expert on the brain. I'm not a neuroscientist. This is going to be very reductionist, but the two big things that I'm thinking about are vagal withdrawal and sympathetic nervous system activity, and how both of those things impact cardiac output and the regulation of blood flow to different areas in the body. So if we're just doing like small muscle mass exercise, we're just like squeezing a hand gripper till failure. It's a really simple task. There's going to be little to no sympathetic nervous system activity ramping up during that activity, and heart rate's probably going to be under 100 beats per minute unless you're really deconditioned. So the flow of blood to those working muscles is more or less going to be inversely proportional to how much you're deoxygenating those tissues. So you start working those muscles, you're stripping oxygen out of the tissues, and then you're going to increase flow in response to that. And that's the process of metabolic vasodilation or hypoxic vasodilation, whatever you want to call that. But once we start getting into like more vigorous exercise, if you're doing like a leg press or cycling or running or CrossFit, anything more complex, that's where sympathetic nervous system activity starts becoming increasingly important. Because if we're thinking about the pumping capacity of the heart, it's finite. It's actually a pretty shitty design. If you look at some of the like super old school exercise physiology textbooks before it was even called exercise physiology, like the work physiology books, they have these like super complex mathematical models basically showing that on paper, like a human being shouldn't be able to stand up, let alone do exercise, because we don't have enough blood in our body. In our heart's not powerful enough to maintain our arterial blood pressure. Like the pumping capacity is just so finite. But what makes all of that possible is that our sympathetic nervous system regulates our blood flow by constricting areas of low metabolic activity that allows us to get blood to more important regions. So when you talk about like the respiratory system in the brain, well, if your respiratory muscles are doing a lot of work, it's a lot more important than a muscle in the periphery like your forearm or your quadricep. So you're going to shunt more blood to those respiratory muscles, and by virtue of that, you have to have less blood in the working muscles. So there are these like inverse relationships between respiratory muscle blood flow and skeletal muscle deoxygenation in the periphery. And that's the big interplay that I'm thinking about with the brain. I'm sure Pat has other things to add to that, but that's kind of like the starting point of like getting into integrated physiology. It's like what impacts blood flow, mechanical factors, metabolic factors, and the sympathetic nervous system. And at any given point, those three things are kind of like tugging on each other, and one of them has to win out.
I think that's a great just like analysis and big picture topic heading. You know, just to kind of piggyback off of that, one of the things I've always been impressed by is the timing and sequencing of the way that systems will work together to really maximize utility and output. And, you know, when I think of sympathetics, I also think of the adrenal gland as well. It's kind of like such a tag team. And, you know, in response to exercise, like the most immediate response is going to be this, when we're talking about large scale global exercise, this was kind of differentiated from like isolated, very peripheral, small exercise. But bigger exercise, the first thing that's really going to happen is going to be a neural response, and you'll have this sympathetic output that's going to be taking place. And when you look at the you know, norepinephrine and epinephrine that are going to be excreted sympathetically, they're usually found in a ratio of 80-20 in favor of norepinephrine over epinephrine as they're flowing out from just a purely neural perspective. And when you talk about the differences between norepi and epi, you know, it really comes down to the receptor that they're able to bind to at the level of the, you know, of the vasculature in the periphery. And, you know, when you talk about, there's alpha receptors and there are beta receptors in the periphery for these adrenaline-based compounds. And when you talk about norepinephrine, it's only able to bind to alpha receptors. And really the receptor is what dictates the response of the vasculature. And the alpha receptor is going to create a constriction response. So the primary job that the sympathetic nervous system creates primarily a constriction response. So the first thing that you do is shunt blood from like your reproductive system or your digestive system at the initiation of exercise, which makes a ton of sense. Like you really don't need to be worrying about reproducing when you're running away from a tiger. But you do need to immediately make blood and fluid more available to the peripheral muscles to be able to power you. Now, what I find really interesting is that in a slower sense, we're talking, you know, matter of seconds for the sympathetic nervous system, and possibly a matter of like, you know, up to a minute or minutes when you really get down to the adrenal gland in terms of how powerful it is. But the adrenal gland is going to pump out the same chemicals in norepinephrine and epinephrine, but it does so in the opposite ratio of it being 80% epinephrine over 20% norepinephrine. And epinephrine has this ability to bind to the beta receptors, which are the vasodilation receptors. So the beautiful thing about this, long story long, is that the nervous system takes blood away from regions that you don't need it, and it makes it available to the regions that you very much need it, which is going to be the skeletal muscle system. And then you have this secondary response chemically of bringing this wave of, you know, a large amount of epinephrine to the skeletal muscle, because that's where blood is now being directed. And this very high level of epinephrine will bind to beta receptors and cause a further dilation response, so that we're able to really maximize at that point with prolonged activity the ability to fuel those muscles and get more blood and oxygen to those systems. So I've always been impressed by, you know, sequencing on that front. The other thing that I think of when it comes specifically to the cardiac system in the brain is, you know, Darwin had a secondary book, which was like, I can't remember the exact title of it, but it was like, it went into the emotions of animals and their specific postural responses to those emotions and vice versa. But he spent quite a bit of time talking about the cardiac system in there, and basically said that the communication between the brain and the heart is like just so interlinked, it's unbelievable. So that really, like, as your heart rate rises, it's going to be sending such a strong signal to the brain that the brain is going to be interpreting. And, you know, your perceptual experience is going to be so strongly based on your interpretation of this cardiac data. And it's pretty stereotypical for the most part, where we're going to have, you know, increased feelings of panic or fear or anxiety, something along those lines. And, you know, the more that you work with people, the more that you can witness this with exercise, where particularly, I mean, you have to desensitize people to this essentially. Like when people begin exercise, they just freak out, like people that are out of shape, because they're not familiar with this kind of environment to exist in. But you ultimately can learn, you know, what it is that it means to exist at that level of intensity with exercise. And I find that like providing other bits of information for the brain are really helpful. And I think that's where, like, you know, basically biofeedback becomes so important, with even being able to display heart rate to someone. So it's like, hey, this is just what 150 beats a minute feels like. Okay. If you didn't see this visually being presented back to you, like, you wouldn't be able to interpret it appropriately. But the brain oftentimes needs more information, so that it's like, you're not going to die. This is just what it feels like to be at this level of work. And this is the experience that you'll have when your cardiac system is at this point. So you really almost can't separate the two in terms of the emotional responses of the animal, the arousal, the perception to that arousal. And that communication is so instantaneous, it's pretty incredible.
Evan, you have anything to add? Please go ahead. I'm just listening.
Yeah, so there's so many like interesting strings in there that I just want to like pull on. So going like way back to what Pat had mentioned a little while ago about the circulating epinephrine and norepinephrine, one of the really interesting things about this is that it leads to like one of the great almost like paradoxes in cardiac physiology, where we know these circulating chemicals are going to change the inotropic state of the heart. So basically changing the myocardial contractile state, and it's going to cause more calcium to be dumped into the myocardial cell, and that's going to increase the strength and contraction, and that's going to cause a greater stroke volume as well. So we know what the importance of stroke volume is, but one of the things that becomes so perplexing now is that the strength of contraction dictates the stroke volume, in the end diastolic volume dictates stroke volume, but stroke volume dictates end diastolic volume. So like all these things that Pat's talking about, where we're trying to get blood to the periphery and we need it for doing this work, it becomes such a clusterfuck because these chemicals are causing us to eject more blood from the heart and get more of the blood to these peripheral tissues. But by virtue of that, less blood is in the heart. So these things become determinants of one another. And this is where we start to get into like other really interesting concepts. Like I know, Sean, you had sent over like a list of some topics that you want to chat about. And this is like the perfect transition into like these muscle pumps, because in order to understand how cardiac output and end diastolic volume, or preload, if you want to call it that, essentially how much blood's in the ventricle before the heart contracts, if those things are determinants of one another, which inherently makes very little sense, we basically need to understand that the heart can't increase its own outflow. Like that just doesn't really work in a closed system. So now that we're getting all of this blood to the periphery and we're vasodilating these tissues, we need to have some kind of adjustment in the peripheral tissues to get blood back to the heart from those vasculature beds, because our arterioles are our primary resistance vessels. So the arterioles could increase their radius and diameter by multiple folds. And if all of that blood were to just pool in our tissues when we're doing exercise, like we would outstrip our cardiac output so quickly and probably fall down and hit our heads and die. So there is like a Darwinian evolution perspective to these things as well, where if this didn't work, we wouldn't be existing right now. And one of the big adjustments to get blood from the periphery back to the heart is that the skeletal muscle pump could force all of that peripheral vascular volume right back. So the only way that this system works is if we actually have like another heart in our muscle. So you could almost think of like the heart pumping blood out, but then we have another heart on the venous or return side of our circulation, and these things are constantly cycling blood back and forth to one another. So like we've kind of started with this small muscle mass exercise, and Pat brought it to full body exercise, where you're really pushing your cardiovascular system, and like it's terrifying, it's painful, and you have all these sensations going on. And it's interesting because it almost scales linearly with like the more sensations of fatigue and pain and all these feelings that you're getting, you're also scaling up the complexity of feedback loops and regulation that's going on as well. And I have to believe there's some like causal link between those two things. Like the more you're pushing your body, the more systems you're tapping into to make sure you could keep yourself conscious and functioning. And there is some level of threat inherently in that. So it's just like interesting how all these things kind of tie into one another, and it's just this really complex and dynamic system that we're dealing with.